Good afternoon. Hope everyone had a good lunch. We're ready to start session B, Technologies, Software Docking and Communications. Craig Burkhardt and I will be your hosts. Just a reminder to our speakers, you have each talk will be 15 minutes, and we will give you a notice at the 5, 3, and 1 minute mark. And we will also have a question and answer session at the end. So if everyone can save their questions until then. With that, let's get started. Our first speaker will be Massimo Biella and his talk is titled On the Feasibility of Quantum Docking for CubeSats.
So, thank you. I'm Massimo. I'm a master's candidate at the University of Arizona and the Space and Terrestrial Robotic Exploration, or SpaceTrex Laboratory. And today I'll be talking about quantum docking for CubeSats. So in the presentation, I'll go over some introduction and motivation for the existence of this project, some related works for what people have done in the past, and then we'll see what we are trying to achieve with our research in this field, the challenges that we'll have to overcome, and then some concept of operations, a brief overview of what flux spinning is for maybe some of you that might not be familiar with the physics of it, and then how we plan on getting or performing our research, basically. And then I'll just touch on what we're planning on doing as long as future work goes. So starting with a motivation, we've been seeing in the recent decade or so an exponential increase in CubeSat launches. It was estimated that in the next 6 years, we'll be launching 2,500 satellites, which is more than the 1,600 that we've been launched as of February 1st, 2022. So it's quite a massive growth we're about to see. And what that will allow us to do is it will allow us to build in orbit assemblies of CubeSats to basically construct, in a way, scientific and commercial platforms. And in order to do that, we need to be able to provide some, or we need to be able to dock these satellites so they can communicate with each other and make sure that they stay in place, basically, where they're supposed to be. And so flux spinning provides, flux spinning represents one of the non-contact docking mechanism or technologies that our lab has been working on. And what that does is, or non-contact in general, what that does is it eliminates some of the risks associated with conditional or traditional docking techniques, such as like mechanical failures or leaks of any sort, and at the same time providing very high mechanical stiffness. So I think a study by Shore and Peck was estimating that only for a few 100 grams of material, they were able to achieve a mechanical stiffness of 200 Newton meters. And so another one of the advantages that these technologies have is that they don't require any kind of voltage or power supply to any of the two spacecrafts. And so in terms of related work, so this is what people have done in the past. So in 2009, you can see here, this is sort of a brief overview or some sample mechanisms that were proposed to use with this flux spinning technology. And on the top, you can see two CubeSats flux spinned, represented by that little gray line there. And what Shore and Peck were trying to demonstrate is that flux spinning basically fixes the modules at their initial and end state and not in between. So what that allows us to do is we can turn off the flux spinning interface, or which we usually refer to as FPDI, or flux spinning docking interface, and use some other kind of actuator to basically rotate the satellite or move it into a different position, and then reestablish connection to flux spinning into the step you can see here. Or in step B, we can select one of the other advantages of this technology is that we can select degrees of freedom that we want to constrain. So the technology allows us to constrain it in 6 degrees of freedom, any kind of satellite. And so we can leverage that to our advantage. So you see here, for example, in example B, they basically showed how a hinge could could be created using this technology. And then you see some kind of like morphing rotating structure was showed with the same principle. On the right here, it was a study from 2012 by Young. They basically wanted to see, they considered a pair of actuation magnets and superconductors. And what they wanted to see was what kind of effect the magnetization of the superconductor had on the force parameters of the interface, of the superconducting interface. And what they found was that the superconducting interface forces are very sensitive to the magnetization of the superconductor, as well as to the amount of current and the direction of the current that is supplied to the actuation magnet that you can see on the right. So blue pins next to the superconductor. And in this experiment, they used permanent magnets, so they were not able to control how much current was supplied to the magnet. And so they found out that the actuation field was too weak for the flux spinning to actually be able to keep the two satellites, or to have any kind of self-stabilizing features. And so what they decided to do was to use electromagnets and be able to control, the current flux through the magnets. They were able to find some optimal value that would yield, basically would keep these two modules docked between each other. And this is basically just another concept following some of the same physics. And this is kind of an experimental bench test that we're trying to recreate as part of the future works. And so some of the objectives we have with this research is we want to be able to develop some algorithms to manage the morphing of structures in orbit. We want to be able to rendezvous, dock, and then release two or more 3U CubeSats in the Earth orbit. And we have to pay, one of the constraints we have is that we have to take into account the different kind of electromagnetic interferences that the CubeSats will be subject to. Given we're on the Earth orbit, we'll have definitely Earth magnetic field playing a role, solar pressure. And so we'll have to take that into account. And so here is just a brief schematic of what that will look like in our imaginary, at least. Some of the challenges, again, like I said, electromagnetic interference is probably one of the biggest ones. We're playing with magnets, electromagnets, superconductors, so we have to be careful. We have to be careful about the amount of current that we're going to supply to the magnet. How are we going to keep those fixed? Because yes, we can fix them in 6 degrees of freedom, but we want to make sure that during the actuation phase, or basically when we don't have the two satellites pinned, we want to make sure that the maneuver we're trying to execute is going to execute correctly. So, for example, say we don't want to go off axis, and then the way that the docking occurs while using flux spinning is not as linear. It doesn't really resemble what you would expect or what you would see in a traditional docking scenario. So instead of having two satellites getting closer to each other linearly and then coming to a stop, what happens is, because of magnetic interferences, you have some sort of like oscillation between the two, so an approach. And so that will take some time to reach equilibrium state, and it's an equilibrium state. And that is also why some of the studies that I showed previously introduce damping materials at the front of the satellites to basically try to help and prevent that. Latency is also another one of the problems or another challenge that we'll need to look out for, as if we're not careful with the with this kind of oscillation on approach or on rendezvous, we might risk having a collision. And then actuation. So the thing with high temperature superconductors is that they need to be cooled at very, very low temperatures. Here, usually we're talking about 50 or 30 to 80 degrees Kelvin. Most likely, we're looking at 50 to 80 really realistically for the materials that have been tested so far. And so that is another challenge. So we need to be able to cool them through liquid nitrogen or some kind of other cryocooling technique. So in terms of concept of operation, the first thing we'll want to do is perform an initial rendezvous. And here, What we'll do is we'll use VLC or visual light communication that we'll explain later by one of my colleagues. Uh, and how that happens or how that works is we have two satellites, a chaser and a runner. We have one of the two trying, or we actually have both of them trying to establish contact with each other. And you can see that when they establish contact, the LEDs present on the sides of them start blinking in at a different frequency. And so every stage of the rendezvous up until docking uh, will be corresponding to a different frequency of LED blinking. Now here you'll see a hard docking because this was an animation used for a different presentation as well. But aside from that last stint, the initial rendezvous will happen pretty much the same way. And then we'll actuate the flux spinning through the electromagnet. So what is flux spinning? A simple way to think about it is a normal superconductor, or what it does is it usually tends to repel magnetic fields or weak magnetic fields. In this case, though, we're using very thin superconductors, high temperature superconductors, which means that uh, in presence of a magnetic field that is strong enough, they yield or they allow some flux tubes basically to penetrate the material through the grain-like structures that make it up. And so what that allows us to do is to basically, as you see in the animation on the left, to trap the superconductor into space, basically, uh, into 6 degrees of freedom. So it's not gonna be able to move in any degrees of freedom unless we want it to. And yeah, I have a cool video from the Tel Aviv University in 2011 where they show sort of how that works. And so you can see that the person is providing an initial and an end state. And what the flux spinning does is just keeps the body where it is left. Doesn't require any power. The only thing we'll have to take care of, like I said, is basically cooling the superconductor to a low enough temperature that it is able to be penetrated by these flux tubes, right? And so again, we're planning the mission we're thinking, the mission concept we're thinking of starts with performing an initial rendezvous, usually in visual light communication, as I said. We then cool the high temperature superconductor below its critical temperature uh, with liquid nitrogen or cryocooler. Usually nitrogen is preferred because it's for cost reasons. I think sells for 30 cents a liter versus other people are proposing helium, but it's economically is not as feasible as I think it goes. As of a year ago, it was selling for $5 a liter, and so nitrogen would be a preferred choice. And then we need to be able to control the electromagnets in order to ensure the correct interaction between the chaser and the runner satellites. So here you can see in the diagram, we have 3 magnets on the chaser satellite. And here we have a plate, basically a tank of N2 that is cooling down a plate of superconductor material until the superconductor is able to be to allow the magnetic flux to penetrate it, basically. These are two kind of preliminary models of 3U CubeSats that we're planning on developing on or using as a platform. And so we have your usual solar panels, thruster, we have an integrated ADCS system, antenna battery, cooler plus the HTCS, which will be sitting at the bottom of this, and a damping material again to sort of mitigate those oscillations on approach. And then an onboard computer and pretty much same components on the other satellite, with the only difference being at the interface here where we're going to have electromagnets instead. And so in terms of conclusion of future work, we want to be able to develop this, but we're still in the very, very early stages of development in terms of sizing and system design. We think that flux spinning can lead to very new levels of non-contact interactions between spacecrafts and will enable different kinds of applications in the future. I think we'll have another talk tomorrow about how this can be used for different applications in space. And then one of them, and there will be a segue for another talk that we'll be giving later today or tomorrow, I think, is we were thinking if we have the satellite and it is already cooled at a temperature that allows flux spinning to even happen, then can we use that? So basically, can we use the fact that the satellite is already cool uh, as a sort of like a cryogenic capsule? So what our lab, one of the projects that our lab is working on currently is the lunar arc storage, where they're planning on storing biospecimens or cells onto some lunar base, basically stored cryogenically. And so what we're thinking is, well, the satellite is a little bit cold. Might we be able to do the same thing in orbit instead of doing it on the surface of the moon? And so that's something that we're exploring as well. And I think that's it. Thank you for your attention, and I'll be happy to answer any question. Okay, perfect. Okay.
Okay, I'd like to introduce our next speaker, Anthip Tirupathy Raj, from, he'll talk about entitled Visible Light Communications Between CubeSats During Close Proximity Operations.
Good afternoon to everyone. I am Atip Raj. I am from the Space Treks lab at the University of Arizona. And I'm going to be talking to you regarding VLC communications between CubeSats. So quick outline of what I'm going to talk to you about today. We're going to go about the motivation for this project, then my proposed solution concept, why we chose this, some advantages for this, and then where we are at, and then I'll close out with some future work. So the introduction for this project, we want to talk about coordination, cooperation, and formation planning. I think a lot of the previous talk, and especially the panel, they were talking about need for new types of communication between inter-satellite communication or communication between satellites itself. Why we need that is basically one of the major things that we are focusing on at our lab is to talk about space commerce, basically trading goods and services between CubeSats. This has happened a lot for several decades in large satellites, especially with the International Space Station and the rendezvous and docking with the ISS itself. But we feel like the potential for CubeSats to do the same is missing. Then we also have to talk about in-space assembly. We have a few talks from our lab itself lined up on that. We will talk about that during that time. And then obviously rendezvous, proximity operations, and docking. That is one area where CubeSats potential is still not yet realized. And then swarms. So for this, we need some method of communication between the different CubeSats itself. So yeah, the point is we need a CubeSat form factor inter-satellite communication system, which is not exactly going to be the same old RF communication system that traditional satellites use, and why I will be covering in this presentation. So my proposed solution, or our proposed solution at the lab, is visible light communication, or VLC. It's not a completely new system that is going to go in space. It has been done on Earth before. I will cover that later. But it's basically encoding messages in visible light bandwidth instead of the usual RF. And you see the spectrum over here. So the inspiration for this is that it already exists in nature, and we have done this on Earth as well. For example, as you can see here, the mantis shrimp, it basically uses circular polarized light to communicate messages in the deep sea. And then this is the anglerfish. It uses bioluminescence to attract prey. Then we have a few other deep sea applications as well as forest applications. The bio community still doesn't know exactly what these lights mean. They think it is for coordination because Usually that's what follows after the bioluminescence. And then we have the man-made visible light communication method as well. This is not exactly communicating messages in the form of bits, but it is using strobe lights for visual navigation. So yeah, that's the inspiration for the communication method that we are using. So some related work that has been done so far, visible light communication is actually a standard in aircrafts as well as in the sea itself. It's not yet a standard in space. But yeah, we see the SpaceX Dragon using the similar blinking lights as well as the red and yellow navigation lights that you see in aircraft, actually. The space shuttle did not have this as a standard. They got the FAA clearance to not use blinking lights, but apparently SpaceX, it's cool to see that SpaceX uses blinking lights. And the one in the bottom you see is basically the actual visible light communication protocol used by GE. That was actually used to transmit messages to customers entering shops to figure out where they are at, and based on their location at the shop, they get different coupon codes apparently. So yeah, there have been standards for existing aircraft and maritime applications. So some of the advantages as to why we are proposing this as a space alternative or an addition to existing communication system is because there are already terrestrial advantages compared to RF communication, basically higher speed, no EMI interference. Then it's of lower cost because it's just simple semiconductor LEDs. Then one of the main disadvantages of RF is that it's getting really crowded. So it's really hard to find RF communication bandwidth, whereas visible light, you have a lot of bandwidth. And then dynamic load balancing is basically sharing the load between RF communication as well as visible light to as a redundancy or as a additional communication method. But obviously, there are some disadvantages for VLC itself. One of them, one of the key ones is the requirement of line of sight. Since it is visible light based, any opaque object can basically block the message. So that's why we haven't seen VLC take off on terrestrial applications, but this will not be an issue in space because the number of abstractions is relatively less. It is also lower range. If you want a higher range, you'll need to go with more power, and the advantage of VLC being low power will go away. But we are proposing this as a method for proximity operations, specifically in the 50 to 100 meter range. So that will not be an issue either. External noise, there is a potential of the sensors being blocked out or being saturated by the sun. So we are trying to combat that using optical filters. So yeah, getting the best of both worlds using VLC. So based on all of this information, we plan to come up with a system to identify 2 3U CubeSats in space. We start at the low Earth orbit, and then we plan to apply this to deep space as well. Obviously, it has to fit in a CubeSat form factor. We have just chosen 3U as the baseline. And then we have to develop the system to encode messages, to transmit messages across 50 meters and have a data rate of 100 Mbps. We have chosen 100 Mbps as the baseline because the sensor, the LiDAR sensor that we use at the lab has a data rate as 80 Mbps. So we want to transmit attitude messages between 2 CubeSats. So it's a similar animation as to what my previous presentation showed my colleague with a few extra messages. So this is basically the deployment sequence of the 3U CubeSat that we envision. And as you can see at the bottom left, we have the frequency messages that my colleague talked about. So initially, you have blinking lights as lighting cues. You have 1 Hertz as a searching mode. I'll explain the 1 Hertz and the 2 Hertz in the next slide. But basically, it's like as you get closer, the frequency of blinks get faster. And once you get into 5 meters to 10 meters range, you actually start high data rate communication. So yeah, active lighting cues. Basically, we are embedding the exterior of the CubeSat with several LED lights, high power LED lights. These are not the regular low power LED lights. These are like the SMD LED, COB LED lights that you use on headlights in the vehicles nowadays. Basically, 1 hertz means one CubeSat has not seen the other, so they are searching still. And if one CubeSat is going to be in this mode for more than a particular amount of time, then they will execute a manual spin so that the other one will find it. So you're using a combination of LED lights and photo detectors to first recognize the other target. So then the second is basically 2 hertz. That's when one spacecraft craft has seen the other. And then once both of them are at 2 hertz, you start 3 hertz, and then you use propulsion to get close to the other. And that's when you start ranging with LiDAR or radar or any other ranging method. Then you start transmitting messages using VLC. This is a quick overview of the design itself. We are planning to use COTS products for our initial prototyping and bench testing. The sensor and the LED light that we are using are very easily available commercial products. And let me go through quickly the architecture of the CubeSat itself. So the dotted lines, as you can see, are the 2 CubeSats. They have a simple Raspberry Pi microcontroller right now. You use them to you use that to modulate the embed messages, modulate it, and then send it through an LED driver. And then the other CubeSat is going to have the photo detector. You pass it through a filter, and then you decode the message. So we have finished some of the prototyping initially at the lab. We have a light adjustable lighting studio with which we plan to do some testing. So this light adjustable studio is capable of simulating different conditions or lighting conditions in space. So let's say we can simulate basically complete darkness as to when the spacecraft is in between Earth and Sun, as well as complete brightness, as in when the spacecraft is in between the Earth and Sun. So we can simulate both eclipse as well as the sun condition to see what are the advantages and the disadvantages. We have a LiDAR in-house. So based on that, we get some ranging data. We want to, the final objective would be to basically have 2 CubeSats communicating their relative distance using VLC. So yeah, conclusions and some future work. So some of the fabrication of the LED circuit has been done. Ranging has been done. So we are in the process of integrating the ranging circuit as well as the VLC circuit. Once that is done, we plan on doing some hardware testing and plan to raise the TRL that way. With that, I will conclude my talk and take any questions right now or after during the panelist one.
So we have a few minutes. So any questions for the speaker? If not, we'll just move on to the question and answer phase later. Thank you. Okay. Next speaker will be Leonard Vance, and his talk is titled Development of a Generic Grappling System Utilizing Shape Memory Metal for Object Capture.
Okay, this is work done by myself and an undergraduate researcher, comes out of University of Puerto Rico and David Vargas Villanueva, underneath this asteroids laboratory with Dr. Thangapathy. Let's go on. All right, I guess I get to do this, right? Okay, so the space grappling problem, probably everybody in this room is reasonably familiar with, right? This is something which has been around for a good 50 years, and everybody has come up with various ideas on how to deal with it. There's nets out there, nets on the end of tethers. There are multiple robotic arms for attaching and holding, and there's more recently, and I just saw this in the last month or so, you've got another group out there using electrostatic pads on multiple grappling arms going around objects. But the basic question is, how can you grapple something that is an uncooperative object. So it's got it's got some spin rate associated with it. It doesn't have any places to attach necessarily. How do you do it in a generic sense if you want to do, for instance, orbital debris removal? Now, I did this particular work trying to figure out how to grapple regolith around an asteroid, but it's a generic problem, right? I mean, and the more immediate one is that we've got a whole bunch of stuff up in sun sync orbit that needs to come down. So what we're going to talk about is an approach that I've been working on with some folks for a little while now that involves at least a pair, probably 3 set of independent links. And each one of these, and I don't have a pointer here, so I'm going to have to do the best I can by just pointing. There's a whole bunch of links that are associated with each one of these grappling arms. Each one of them has independently controllable curvature associated with it. So if you look in the upper right-hand part there, there's a worm drive and you have a 1D control. So each one of these segments can be independently controlled to curve around an object of indeterminate size and shape as it's going on. And you can see the 2-dimensional concept in the lower right-hand corner that was originally thought through. So what this is about is mostly the tool that we put together to figure out how to see how viable this is and the dynamics associated with that, because I don't think that's actually been done any place else so far. Lots of concepts, not so much math. And as I'm working on this, we got a student that came in with us early last semester, and he had the idea of doing grappling, but he had the shape memory idea. So suddenly, this is I've got this concept of a worm drive and a whole bunch of independent links. He's got a concept whereby you simply heat up or cool down a piece of metal, and it curves inwards or outwards depending upon its temperature. So now, instead of a complex worm drive moving part kind of problem, you've got more of a continuous thing that you just heat up. And so the number of moving parts, I guess you have to define what a moving part is in this context. But now it's a solid state approach instead of a mechanical gear kind of approach. And so although you don't actually get to see the movie doing this, when you heat up this material, it opens up like a flower, and you let it close back down again, it comes back exactly where it was before. So you could see how this might work from a grappling standpoint. And he'd worked out a technique whereas you've got a heater on one side and a Peltier cooler on the other, so you can artificially heat up or cool down to get the shape that you want at the time that you want it. So that's the basic idea. But now we need to kind of model this, because the question is this kind of thing going to work at all? And so this is the approach. It's a multi-body simulation, and in this particular case, there's 19 elements on either side of these grappling arms, and each one of them is a 6-degree of freedom simulation, which is linked together, and then you have the ability to actuate each one of those 19 links on either side and decide what you want to do in order to enclose something or not enclose something, or hold it or let it go, as the case may be. So you've got to model all of that, plus you've got to model the debris object that you're trying to capture. And so I'm going to do a relatively simple job of that, but you're going to get an idea of how the model would work. Now, 5 years ago, I was an engineer doing a lot of the same kinds of things you guys were doing, had some spacecraft that were going up, but now I'm an academic, and so academics have to do math. So you're going to be forced to deal with a little bit of linear algebra here that goes along with this particular problem. I'm going to use this 3-link model as a baseline, and what we're going to do is, I'm going to show you how I derive what the forces are that keep those links together so that you can model them as a set of 6-degree of freedom rigid bodies. No surprise here. Those of you who are into dynamics will recognize that this is just the simple 6-degree of freedom rigid body dynamics equations. And I guess what I'm trying to point out is that on those links that you saw previously, there's an A side and a B side. So let's talk about that just for a second. Is it possible to go back? It is. So the scenario is that you're trying to come up with the forces that hold each one of those links together. So first thing you got to do is figure out what the accelerations on those links are, given that they aren't held together. Then figure out what forces are necessary to hold them together. And so that's why that A is there on the left-hand side. That's the acceleration as a result of force on the link, and then the angular acceleration down below. So I'm going to assert the existence of a matrix. Now this matrix H takes you from the force at the end of the link to the delta acceleration at either one end or the other. So there's an H matrix for each one. They're 3x3s. And so you can relate the motion to the forces that are in place, and then you can put it together into this lovely large matrix. And so this leaves you to understand what the acceleration of each one of the ends of the links are on the left. And you know what the relationship between the forces and the accelerations are because that's derivable from 6th degree of freedom dynamics. You don't know what the forces that are holding them together, but you do know what the accelerations are if they're just allowed to float freely. And so you're trying to get to, you got a basic problem. You've got unknowns on both sides of the equation. So how do you solve it? And you'll do this with linear algebra. So you'll notice that the force at the end of one link is the negative of the force on the next link. So you can equate those two together, add them up, it reduces the number of equations and makes it homogeneous on the left-hand side. So that's the mathematics that basically gets you to the bottom. You invert that set of H matrices, and then you've got the forces that hold the links together. And then when you apply those, you're independently executing 39 different 6th degree of freedom simulations with those forces. And if you've done it all right, they all hang together and they don't move apart. And that in fact is the case. And I'm going to not show you that particular chart, but show you that energy is conserved. I did a case here where you simply opened out the grappling arm, bent it back a little bit, added some energy, and then watched it move back and forth. And you can see with the damping and the system off, the energy is conserved up on the left-hand chart, and you turn the damping within the links back on and it decays over time. So it's behaving the way that you would expect it to. Now, we've got to get to another problem now. And so this one turns out to be not as simple as I'd expected. We're going to grapple an object, which means that we have to touch, which means we have to come up with a model with what we are touching and with how much force. And so each one of these points that I've talked about on the grappling arm is going to have a location. And now the question is that going to be inside our debris object or not? Because that means it's touching. How do you decide if a point is inside or outside a polyhedron? And I've used a tetrahedron here because that's the simplest possible case. But the basic trick, if you haven't done this before, is you run a ray right down the x-axis and you measure how many times you pass through a facet on the model. If it's an odd number of times, 0, or 1, 3, 5, that means that you're inside. If it's an even number of times, it means you're outside. If you think about that, it'll make sense. But you work in 2 dimensions first. And so now you have to figure out whether or not how many facets you've touched on the way out, going out that particular ray. And so this is just the technique. You take the positions of the facet, the 3 elements, you figure out where on that plane it intercepts, and you find out if the intersection point on the right-hand chart is actually within that triangle or outside that triangle. And if it's outside, you're not passing through it. Okay, once you've done that, you now know if you're touching it or not. Now the question is, how much force do you get when you do? Well, the first thing you have to figure out is what's the closest facet that you're touching, because that's the one that's pushing back. And so this is just how you do that on that particular model. And then the force that comes back is related to the the spring, how far in you push, and then there's Coulomb friction that goes along with it. So that's the force model on the contact. So now I've done all of this, a lot of math, and then there's a simulation here which hopefully puts it all together. So here is that grappling system. It's got 19 links on each side. And you'll notice that it unfolds like an accordion. So when I did this, I wasn't working directly with the um, with with the shape memory metal. But when it gets to the second phase, it's equivalent to where the shape memory metal will be, and you'll see that in a moment. And you've got a 8 kilogram object, and it's got a rotation rate of 70 milliradians per second, and this axis, and in the roll axis, it's got 10 milliradians per second, just so that it's tumbling a little bit. And the system is going to try and encircle it, and so you can get a feel for how that works here. The first thing it does is it unfolds, and then it swings back into a spiral here so that it can deploy and encircle the object. And so you can see the dynamics of the underdamped system. And then as it goes around, basically every time it touches an object, it moves the link up further until it completely encircles it. And so then that manages to hold the object and get it secure after a little while. This algorithm is just getting started. There's a lot of other things that can be done with it to make it work more efficiently. Obviously, I should be using more points within the grappling arm itself, because you can see that it's actually looking like it's inside the corner of the debris object there a little bit. But that's the, with more points modeled, that becomes straightforward. So as a summary, we've got a basic model to do this. The algorithmic approach has been verified to be working correctly. We're in a situation where we're close to being able to evaluate the basic capability of these systems, of this type of system, and whether or not it can really work in a generic environment. So with that, I think I'm about done. I'm out of time. And so do we do more questions now, or do we do questions later? Very good. Thank you.
I'd like to welcome our next speaker, Dennis Ogby from the Jet Propulsion Laboratory, who will speak on anomaly and interference detection for space radios and IRIS.
All right, hi. Let's see. Good to go. All right, hi, my name is Dennis. I work in telecom at JPL, and I'm going to talk about anomaly and interference detection for space radios and the IRIS radio. And so really what I'm doing with this talk is I'm going to kill two birds with one stone. First going to talk about IRIS and some features that were added to the IRIS radio. And then I'm going to talk briefly, you mentioned the NASA standard 1006, which kind of inspired some of the work that I had more to do with, which had something to do with interference detection. I'll sort of go into that during the talk. So very briefly, what's the IRIS transponder? Everybody's probably familiar with it. It's JPL's lowest swap coherent transponder that's targeting CubeSats. It's being used by a lot of missions. We've already heard it mentioned quite a bit during the previous session, also during this session. A lot of upcoming missions are using it. So I sort of here's a list of the current missions that will be using the IRIS transponder. And so in terms of recent updates that were added, so I think there was a talk on last year's iteration of this conference. And since then, there was some features that were added. So one thing is one-way ranging with CSAC. I think we heard that in the talk on Capstone. Then there have been some improvements in the carrier acquisition system. So there's just sort of a new FFT-based carrier acquisition, which allows the acquisition of carriers sort of very far away from the best lock frequency, which means that you don't have to sweep anymore to try to find your carrier to lock on, which saves you a lot of time. There's a new, what we implemented is a multi-stage carrier acquisition system where you can change your PLL bandwidth from a wide bandwidth as you're searching for the carrier to a narrow bandwidth when you're tracking it. Overall, all of those changes resulted in the carrier being able to be acquired in about a second, which is great for operations and also very good during testing. So you're not sort of have to sweep the carrier. Very good. Another feature that was added was uplink encryption according to the CCSDS Space Data Link Security Protocol standard. Another thing that was added to the firmware was a SpaceWire CNDH interface. It used to be SPI, and now it supports SpaceWire, which I think helps in sort of downlink telemetry rates. LDPC coding was implemented, and there's also a implementation of pulse shaping. So pulse shaping is becoming more important. And the pulse shaping implementation in IRIS sort of adheres to both the NTIA and the SFCG masks. And then overall, kind of due to proper comm engineering, there was the implementation loss of IRIS was brought down to about 0.5 dB. So I personally did not have that much to do with these, but they're available to be integrated. So if you're more interested in these features, I can sort of get you in touch with the right people. So switch gears a little bit. These are the recent features. One interesting one was sort of the encryption capability, and that's speaking a little bit in terms of where things are going. One of the recent push for security resulted in the NASA standard 1006, which is a safe space system protection standard, which calls for increased security for NASA missions. And so technically, I think all projects established after 2019 have to implement this, but I think there's a lot of ways around it, so probably not. But going forward, it's become very important to sort of protect your comlink, and it's probably less important in deep space. But they define these 6 SSPRs, space system protection requirements, that sort of protect your command stack and don't let your spacecraft be hacked. The most interesting one, at least for this work, what inspired this work, is the work on interference reporting, which sort of is a requirement to autonomously detect any interference and convey that information back to the ground. And so, this inspired us. How could we do this in a transponder like IRIS? How could we implement this? And so we thought about this and sort of came up with a simple idea of how to do this. Your traditional transponder like IRIS, we have a desired signal coming into the antenna, going through an RF front end. These are all software or firmware defined radios. So we go through an ADC, and then we do all the tracking and firmware, and then sort of the command handling and software. How would we detect interference in this scenario? Is our concept here is to add into the firmware the capability to record the raw samples directly at the ADC, save them somewhere in memory, and then use software to detect any anomaly in these samples. So there will be a detection algorithm that hopefully can be trained offline, either on synthetic data or on recorded data. And so that's sort of the overall idea. And then these type of algorithms that detect interference sort of fall under the larger class of anomaly detection algorithms. So we define an anomaly as if there's the desired signal and the interference, and we define no anomaly if only the desired signal is present. This task then really was kind of 2 parts. The first part was to infuse an IQ recorder, a sample recorder, into IRIS. And the second task, somewhat separate to this, at this stage, was to study the detection algorithm and to study a detection algorithm that could be implemented on a rather sort of low software power radio like IRIS. So first, talk about the IQ recorder. This is part of this task. There's really not that much to say. It was work done to do it. It was integrated. The firmware appears to be ready. There's still some software that needs to be written to actually extract the samples, but overall, we now have sample recording capability in IRIS, which is useful for this. Here's sort of a larger block diagram of how this looks. Data gets read out of the ADC into memory, and then it can sort of be extracted over the CNDH. So this is ongoing, but this will be available soon, probably after this fiscal year. Switch gears for the rest of the talk. I'm going to talk about the actual detection method. And so again, we tried to study something that was simple to do and simple to implement, because we don't have a lot of compute power right now on our deep space radios. And so what we wanted to do, we first sort of defined the playing field. So what do we want to detect? And the goal here was, at least for this task, is to detect 3 flavors of interference. I drew some pictures in MATLAB. So we have the signal on the top left is just signal without interference. Time axis is going into the slide. And the three interferes that we care about is like just a constant tone. You know, what if a constant tone shows up in your main lobe? And this could be this is the easiest one to produce. So if you were an actual jammer adversary, you could just put power on a tone and try to jam me. But this could also come up from, let's say, a malfunctioning instrument, which is something that apparently, as I've been told, actually happened on the Electron MRO, which had a well, actually, I think it wasn't malfunction, it was misconfigured or something like this. But there was mysteriously during integration, a tone showed up in sort of the main lobe of communication and caused a bunch of mayhem. So this is a story I've been told. I was not there for this, but it's a real problem, you know. And the next one that we cared about was a linear chirp, which is sort of model a walking tone, which it still sort of covers a wider bandwidth. If you were an adversary, you could generate that pretty easily. But it could also sort of model something like a power supply or something like this. And then the third interfere that we care about is band limited noise. Just like, let me just give you, let's say, a megahertz bandwidth and just like put a bunch of power in that. So these are the three interferes that we studied. The actual detection algorithm, I'm not going to go over this in detail, but essentially the idea is we wanted a simple algorithm. We want to do something that, you know, does not require a massive neural network or something, or like an LSTM or, you know, this big powerful machinery. And so the idea for this algorithm was, okay, we have access to non-anomalous data. Let's learn it. Let's learn the covariance matrix of it. And then use that covariance matrix, save it somewhere. And then how we detect an anomaly or interference will be, okay, we take the covariance matrix of non-anomalous data, whiten any observation that we want to test with this covariance matrix, and then compute the power of the whitened sequence and apply threshold. So it's a very simple algorithm. It could be done maybe on idle time or something like this. And so that's what we're studying in this work. Ideally, in the future, there will be more that we can do there with more powerful processors. There might be even fancier things that we can apply here. But that's the idea. Multiply your signal with a matrix and compute the power. So how do we sort of measure how this works? We care in this work. We care about what I call the PT over PI ratio, which is the interference to, well, it's desired signal to interference power ratio. So we have in blue here, we have the desired signal, and so what we really care about in this study is the ratio between them. And then we can assess the detector performance. There are many ways to measure performance of a binary classifier. The one that we chose for this was the receiver operating characteristic curve. It's an old curve from radar days, apparently. At least that's how I learned it in school. Great. And what we care about is, I'll show you a rock curve after this. And then really what we care about, sort of fundamentally, the main idea is, okay, I have a desired signal, I have an interferer. The interferer will do some damage to my communication link, right? I'm a communication engineer. So I think about an SNR and my bit error rates. And I can go into a theory for my modulation scheme and compute the bit error rate that I should get for an SNR that I operate in. And I have a jammer. Okay, that jammer, I can measure the bit error rate with that jammer. Presumably that's a lower bit error rate. And I can take the difference of those 2 points. This is I then take the bit error rate and map it back to an SNR. I take the difference in the 2 SNRs and I define that as the SNR loss. And then I can sort of plot the detector performance as the area under the curve versus my SNR loss. And then I can answer the question, okay, if I want to detect my interference with some fidelity, let's say I want an area on the curve of 0.9 or something, how much damage will each of these jammers do to my system before I can detect them with the performance that I want? And so that's kind of what we're measuring in this talk. So let's go through some plots. This is what a receiver operating curve looks like, or this is what 6 receiver operating curves look like. The worst one that you can have is the dark blue one here. I should use this pointer on Zoom. This is the worst in this case. The worst theoretical raw curve is just a line from 0 to 1. The best raw curve is a square where you shoot up to 1 and go to the right. What the raw curve plots is the false alarm rate versus the detection rate. And so in this case, in the best case, you could detect with a probability of 1 and a false alarm rate of 0. So that's what you want. And the multiple lines that I have here are sort of in the dark blue line is with a dominant desired signals, so a very low powered interferer, which is very difficult to detect, versus the light blue line is a very high powered interferer, which is very easy to detect. So that's why this plot makes sense. And the measure then is perfect. The measure then is our sort of metric for the performance of this classifier is the area under this curve. The best area is 1, worst area is 0.5. So then we can plot these for the 3 different interferences that we've studied so far. We can plot these as a function of the PT over PI ratio. And I put some helpers down here because I sort of have to remind myself of which direction is what. As we go to the right on this plot, we have a dominant desired signal. So we have a weaker interferer. As we go to the left, we have a dominant interferer. A few observations on this plot. First and foremost, as we increase SNR, actual base SNR, it becomes this detector that we study becomes essentially almost perfect. As we decrease SNR, we see a very distinguishing pattern. With increasingly dominant interferers, it becomes more easy to detect them. The chirp and the tone behave roughly the same, which also makes sense. And the wide bandwidth interferer is always the worst. So this is sort of one takeaway here. And then, as I mentioned earlier, the discussion, okay, what's actually my SNR loss? Here's one example. There's still more need to study this. Here's one example. If I want an area under the curve of 0.9, and want to compare the tone and the wide bandwidth interferer, I can look at the red lines here for an SNR of 60 dBHz. A tone I will be able to detect the tone with this fidelity at a loss of about 1 dB. Whereas if I take the wide bandwidth interferer here, I'd get a loss of about 2.5 dB before I could detect it with the fidelity that I specified here. So that's kind of the status of this work. There will be more going forward, hopefully some fancy classifiers, but that concludes my talk. Gave an overview about the features that were added to IRIS, talked about standard 1006 and sort of how we think we could implement some of the tasks, really just one SSPR on IRIS. We now have an IQ recorder, at least at the end of this fiscal year, we'll have an IQ recorder that will work. We're studying anomaly detection methods to detect interference so we don't get jammed. Thanks. All right. Any questions after?
Acrobatic. Okay. Our next talk will be by Jeff Levison from JPL, and it's titled F Prime Flight Software Product Line Overview.
All right, now we're squarely in the software portion of the session. Good afternoon. My name is Jeff Levison. I'm the supervisor for the small scale flight software group at JPL. This is a group that is manages and maintains the F Prime open source flight software product line, which is what I'm going to be talking about in the next few minutes. This presentation I originally put together as a 25-minute presentation, so I'm going to be, plowing through this, and we'll see how it goes. Basically, I mean, if there's a point to this, it's to talk about the way we've had to rethink our approach to flight software development because of this changing landscape that's been shaped by the emergence of these small scale flight systems that we've been tasked to support. And if there's recommendation that I just want to give right off the bat is if you're working on these kinds of systems, particularly in formulation, and particularly for a interplanetary style flight system, to think about flight software up front and not treat it as an afterthought. So there, I got my message out in case I get the hook later. So the rest of the talk is basically just about how we've had to adjust our approach to flight software given this changing landscape. And, so first, we have a rich legacy at JPL delivering flight software systems for successful missions at JPL that have been developed at JPL. deep space complex missions where we've, honed this very traditional approach that's worked very well for us for flight software development, where we start where we have dedicated siloed development teams or teams of teams where you have a development team and an independent software testing team that starts off by taking a flight software deployment from some previous project and then acquiring that and then basically adapting it for the exclusive use of the project in under development, creating basically this monolithic software that is completely dedicated to this particular project, and then with absolutely no regard for how the software is going to be used on the next project. And this has worked very well for us. I mean, we've been very successful with this approach, and we've demonstrated with this approach that we are able to meet the challenges associated with flight software for these deep space systems. However, we're faced with new challenges that calls into question this traditional approach. Particularly, our heritage flight software is really not well suited for this new generation of small spacecraft. The processes that we follow, for example, pretty much inherently assume the existence of a large team with a lot of resources, which don't typically apply in the small scale realm. So our processes that we put in place for a large scale system don't scale down very well to address the needs of small scale systems. And then conversely, what I call the university style CubeSat development, given the setting, maybe I could come up with a better name for that. How about the skunks work style? The idea is you take a dedicated small team of really committed and hyper smart individuals, and you throw them in a room and basically say, go to it, just crank something out, and basically leave them alone. Right, that process also can work, but it doesn't scale up very well if the system has even moderate complexity. Although we've been successful with that approach. Marco, right, which is, you can see the model of it just on our table right outside. That was our first interplanetary CubeSat, and that successfully used that approach. And so, what's wrong with that? Why rock the boat there? Well, we're in a situation now where we need to support more flight missions than ever, and that's where both our heritage approach to flight software development and this sort of skunks work style, that's where those approaches start to break down. We have to support a wide variety of missions with a wide variety of platforms. And then on top of that, a lot of these projects come with this willingness to accept an increased risk tolerance with what we call at JPL a type 2 class of mission, as opposed to type 1, which just means type 2 missions are just ones that are willing to take on more risk than type 1. I think with NASA, they're called class D missions. And so there's this extreme cost and schedule constraint that's applied to this category of missions, where all stages of flight software development, especially tests, are heavily compressed. And so while there's willingness to accept more risk at the project level, there's no consensus of how you drill down that risk acceptance down into flight software development, because software is still mission critical and it has to work. So, we've adjusted our approach to move towards a product line approach. And so the F-Prime product line targets small scale in-house missions that are expected to, well, first of all, I should just say that this is not a novel approach that JPL invented. I mean, software product lines exist in industry. It's just that this approach is novel. It represents a paradigm shift for JPL. So the F-Prime product line, it targets small scale in-house missions that fall into 3 categories generally. Small systems like CubeSats and SmallSats, flight instruments, and flight deployables like a Europa lander or a Mars helicopter. Additionally, F-Prime supports testbed and prototyping efforts where embedded software is required, software technology development with an intended path to flight, and collaborative flight software, though, not just with university and industry partners, but also within our own development efforts within JPL with the projects that we have in concurrent development. So the F-Prime product line can support a wide variety of projects and tasks. I should point out that it's not just restricted to small scale. It does scale up to support large scale systems. We don't apply it that way just because we already have approaches that we're happy with. It's the small scale systems that are pushing us in this product line approach. So what is F-Prime? F-Prime facilitates the development of software for embedded applications where typically they're operated remotely and you have a command and telemetry kind of interface with it. It was released in 2017 as open source. It's on NASA GitHub, and the link for it is listed right there. We're celebrating our 5-year anniversary open source this coming July. The product line consists of several elements. First and foremost, there's an architecture, a software architecture that's defined that decomposes a software system into discrete components with well-defined interfaces called ports that are interconnected to form a topology. So this notion of components, ports, and topologies is a major element of the architecture approach. The software systems developed in F-Prime are developed in C++, so there's a C++ framework that's provided that provides basic features like message queues and threading and an operating system abstraction layer that's developed according to the architecture specification. There's a suite of tools for specifying components that connect and their connections at a high level. Then there's autocode tools. I'll talk a little bit more about that for generated code from that. And then there's a growing, essentially, component repository or library that provide core capabilities that are common across most flight systems, like command and telemetry management, memory management, event logging, that sort of thing. And then on the testing side, there's a whole suite of tools focused on software verification at unit and integration levels, including a lightweight ground data system that's part of the product line. It's worth pointing out that F-Prime is managed independently from flight projects. We get a little bit of funding, not a lot, but a little bit of funding from the institution that helps ensure that all the elements associated with the product line are maintained regularly using best practices. Use of F-Prime at JPL is increasing. It's flight proven. It's flown on the RapidScat radar scatterometer that was mounted onto the ISS. It has flown on the Asteria CubeSat, which is a exoplanet finder. It's deployed on the Ingenuity Mars helicopter, currently in operation on Mars. It has completed 28 flights and counting. We're really happy about that. It's baseline on a growing number of projects that are in concurrent development at JPL. A wide variety. We've got CubeSats. We've got mini rovers. We've got instruments, motor controllers. A lot of cool stuff. Some of which is going to be launching. We've got a few CubeSats launching, and so maybe next year we'll be back with some presentations on lunar flashlight and near-Earth asteroid sprout. Its use of F-Prime is spreading out organizationally within the lab. So we're working with a number of organizations that don't have or haven't had developers with prior experience with flight software development. And we've demonstrated deployments in F-Prime on a number of processing platforms and operating systems, including running it without an operating system, which we call bare metal. So this is everything I'm going to say about the architecture, all just concentrated on one slide. There is actually a lot to say about the architecture, and there's a lot of resources available if anybody's interested in finding out more about it. But basically, F-Prime at its core is a component-based architecture. So the software is composed of components, which encapsulate behaviors, and the components have these have well-defined interfaces defined as ports. And there's input ports and output ports associated with components. And when you connect input ports of one component to the output ports of another component, and you put this in a network, you get what we call a topology. And when you generate a binary from that, you have a deployment. And so the components in these topologies are not link dependent on other components, so they can be easily recombined. You can mix and match components into new topologies without having to recode anything. And so that has some powerful advantages, especially if you're working on systems that have a number of test configurations that you need to accommodate. It has a number of architectural features that the architecture is designed for, like rapid development, portability. With the tools that are provided, you get additionally software system analyzability and a lot of testability. On the right-hand side of the slide, it shows the software component breakdown for the Mars helicopter. There's actually 3 deployments that are represented there across the 3 different processors associated with the system. There's 2 that are on the helicopter itself. One is the Qualcomm processor that is the primary CNDH computer, and that's the most powerful processor that we've ever flown to date. And then associated with that is essentially a flight computer, which is a Texas Instruments motor controller, and that runs at a 500 hertz control rate It's doing some guidance as well as controls the rotor. And that runs without an operating system. So it's an interesting study of contrast right there on the helicopter itself. There's a base station that also has the same processor as the CNDH processor, the nav computer on the helicopter. And what that diagram shows is a significant amount of inheritance of the software coming from both our component library as well as some software that's reused across the helicopter and the base station. So when you look at the software as a whole, about 20% of the software was actually software that was unique and manually generated for the project. The remaining code was either just inherited 100% from libraries, or it was auto-generated. And it's worth noting that that these 3 deployments that are shown here are out of 11 total that was generated during the course of Mars Helicopter, because the Mars Helicopter project was really the development of a series of successive test configurations leading to the flight configuration, and each test configuration got its own software deployment. And if we had to treat each software deployment as its own monolithic entity, delivered exclusively for that particular test configuration, which is our traditional approach, we would have easily just blown past the resources allocated to the project for software development. Just real quick, there's a whole suite of tools that are provided with the F-Prime product line that streamlines software development at key phases, from design through integration and test. At the design level with F-Prime, the release of 3.0 in December, we've completely focused on, we've envisioned how we approach software design with a whole software modeling feature, software modeling approach that uses a domain-specific modeling language called F''. Now that's part of the product, where you can define and specify your entire flight system at a high level, your components, your ports, and your topologies, all at the high level, in this FPP specification. And then there's analysis tools and there's visualization tools that are provided, all before you even get to implementation. And then there's a whole suite of code generation tools that support implementation, that generate an extensive test infrastructure. And then it generates a dictionary that is used as part of our integration and test suite that includes this lightweight GDS. It's not required or expected that you use this GDS for ops. The F' it also has a process for adapting to whatever GDS is in use for the project. Of course, what would software be without documentation? So there's a suite of online documentation and papers that have been produced. There's also a supported user discussion forum and issue tracking service through Git issues. That's all maintained by people, F' users within the group. So there's easy access to people who have a lot of familiarity with the product. We use F' for enabling software technology advancement, both that both feeds back into the product line, as well as we use F' to advance software technology into flight. We have a good example. I don't have time to go into it, but where we have an example where we used an RTD project to develop an autonomous planning and execution software technology, and we had a way of just infusing it in an unplanned way, opportunistically, into the Asteria cubes that happened to be in operations at the time, because they were. It was something that was enabled. This demo was enabled because they both happened. The timing was good, and they happened to be using the same framework. We're really encouraged by the education outreach that use of F' enables, use of open source software enables. So we like working with students and universities, and we do this in a number of ways through flight software workshops, through funded research efforts, from internships that we put together, as well as working with students that are using F' for their own projects, like CubeSat type projects or something similar. We are embracing, we try and embrace openness as much as possible when we're engaging our open source user community. So we're trying to do more than just throw software over the fence and say it's open source, go use it. We're to the extent we can, moving our core product line functions, moving that out into the open, so that we can reduce maintenance overhead, as well as foster better collaboration with our growing user community. So in summary, F' is a managed flight proven software product line developed to strategically meet the delivery challenges associated with the growing number of flight and embedded tasks, particularly in the small scale realm. F Prime is designed for efficient collaborative flight software development. That is much more than just here's the software architecture and here's some code, go use it. Hopefully you got that message. And we've demonstrated the ability to advance state of the art for flight software, and we are working on growing our user community both internally and externally to JPL. Just real quick, I mentioned we do flight software development workshops. We have one that's coming up in October. This is going to be done a little bit differently, where we're integrating both participants at JPL with selected individuals from the external community. If you're interested, this is not just a tutorial on how to use F Prime. This is a workshop focusing on flight software development. We use F Prime for the in-class example. So if this is something that interests you and you want to be considered for an invitation, just send an email to fprime@jpl.nasa.gov. Just, you don't have to worry about capturing this. Just, we have a flyer. Just walk out the door, walk 5 paces straight ahead of you, and you can get a flyer, or just talk to me directly. I can set you up. Okay, that's it. We got through it. Thanks.
Okay, Ben, are you ready to go?
I am ready to go. Do you want me to drive, or are you going to drive from there?
I can drive from here.
Okay, fantastic. Well, thank you very much for the opportunity to be here, at least virtually.
Okay.
I hated.
Ben, just a second.
Yeah.
I'll introduce you.
Okay, sorry.
So the last speaker for this session, we have Ben Malafis from Morehead State University. The title of his presentation is Deep Space Station 17, a university-operated affiliated node on the NASA's Deep Space Network for interplanetary small satellite missions.
Very good. I apologize for jumping the gun. I'm so excited about this conference. It is it's my favorite conference every year. Really wish that I could be there with you all. This is the conference that to me is the most focused and the most interesting and the most relevant. So appreciate the opportunity to be with you for a few minutes and update you on the progress on DSS 17. I'd like to recognize my co-authors, Tim Pham, Chief Systems Engineer at the DSN, and Jay Wyatt, who is Advanced Concepts Guru, and my colleague here at Morehead State, Jeff Kruth. So we'll go to the next slide. DSS 17 was originally a 21-meter tracking station owned and operated by Morehead State University. It's been around since about 2006. We primarily did radio astronomy research in the beginning and support for some small sat missions, probably the most notorious of which was the JPL Asteria mentioned in the last talk. Phenomenal mission. It really helped us become an operational station, transitioning from an experimental station to an operational station. But since 2006, we've been doing mostly LEO work and radio astronomy. In 2016, NASA's Advanced Exploration Systems upgraded us to become DSN compatibility. And the idea was that we would become a Class D station for Class D missions. With all the new interplanetary CubeSats being launched and with a fairly highly subscribed DSN, it seemed logical to bring another smaller aperture instrument online to support the interplanetary Class D missions. And so that's our purpose in life. So the next slide shows a little bit about our location. If you're not familiar with Kentucky, we're not really in the South, not really in the East, not really in the Midwest. It's sort of a transition region, but it's a beautiful remote region, and our radio frequency environment is reasonably good. We are in a small town with a university of about 10,000 students. So S-band is pretty horrendous when the students move to campus. But X-band and other bands are still reasonably good. It's a great place to do this kind of work with the one caveat, which is that we actually have weather in Kentucky. So thunder, storms, lightning, and rain attenuation does create a bit of a challenge for us. But beautiful location, and it's worked out quite well. The next slide gives us a little bit of an overview of our sort of previous operations. Again, ground station for small-sat missions like Asteria and some of the Morehead State missions that we've flown. We also have been a test bed for experimental communication systems, primarily for collaborators at JPL. So we've done some work in OMSPA, in autonomous operations, and more recently in disruption-tolerant networking. And we've had a lot of fun sort of becoming a test bed for experimental work that you wouldn't want to take a DSN station offline, or if DSS 13 is tied up. So the next slide provides just a little bit of context. I love this conference and the talks because, literally history was made in 2018 with the launch of the Marco CubeSats and their extraordinary success. So it really, for me, has opened the door to a new era in space exploration, and one that's fostered by, or at least augmented by, small satellites and CubeSats. There are numerous interplanetary small-sat missions in planning, from the NASA PSDS-3 studies to each of the centers planning their own missions. Of course, Artemis 1, when it launches, will actually launch 10 new interplanetary CubeSats. And so there's a lot of need for deep space communications and ranging with a heavily subscribed DSN. And as I mentioned, that really was the impetus for the idea behind DSS 17, which also came from JPL. I should mention, Rob Staley had this idea maybe 10 years ago that universities with large aperture dishes should consider upgrading to become DSN compatible for just these type missions. So in the next slide gives you just a little bit of an orientation where we fit within the proper DSN assets. So we're certainly in between Madrid and Goldstone, not equidistant, a little closer to Goldstone, but it's a pretty good longitude. It allows us actually to ghost track Madrid and Goldstone. And that's helped with our calibration experiments, and will no doubt help with handoffs during operational phases. In the next slide, shows you a little bit of the overview and the approach. Again, our motto is Class D ground station supporting Class D interplanetary CubeSats. And the idea is that we would be a bit of an experiment to see if DSN and JPL folks could transfer DSN equipment and processes and protocols to a non-NASA asset, like a university asset. And frankly, it's been extraordinarily challenging. We ended up developing a lot of hybrid systems, but it turns out that I think the experiment's been successful. Because even though it took quite a few years, we were able to basically implement a DSN compatible system here at a small university. So really, we're a test case for non-NASA ground assets, and there are a number of large aperture stations around that could certainly be considered for upgrades to support these new interplanetary missions. The next slide gives you just an overview of some of the challenges. Becoming DSN compatible, I have to say, is probably one of the most challenging things that we've ever done. It is doable, and we're certainly happy to share lessons learned, and so others that might consider doing this wouldn't make some of the same mistakes. But I have to admit, I was a little bit naive whenever we started this project, because we had been tracking LEO's spacecraft for many years. And I thought, well, maybe we'll go out and buy more sensitive telemetry receivers and a higher power amplifier. And we already have atomic clocks. We have cesium beam standards. Maybe we string those together and invoke voting algorithms. Turns out none of that worked. We had to literally rebuild the entire system from the RF and IF perspective. So we had to build a new X-band feed. We needed a cryogenically cool low noise amplifier. We found one that's a closed cycle system, a pretty extraordinary system. Didn't exist 10 years ago. So it's very new technology. It's made by a company in France called Callisto, and it operates at under 20 Kelvin as a closed cycle system. So it doesn't require all the elaborate plumbing and compressor systems that a typical conventional cryogenic LNA would. So that new technology was one of the enabling technologies that allowed us to get in this business. We had to come up with a KPA, a 3 kilowatt power amplifier. And while that was expensive and took a long lead time to implement, I think the biggest challenge there was the isolation that was required between the extraordinarily sensitive LNA and the extraordinarily powerful KPA, all going through the same feed. So isolation was a real trick there. And I mentioned the time standards. Of course, hydrogen masers are the only time standards in the world that are precise enough for deep space ranging. So a lot had to be implemented, and it took a few years to pull it all together. But we've been successful, and I'll tell you a little bit about the process and the architecture in the next few slides. So the next slide has an overall system architecture, and it's a lot to look at, but it kind of breaks down into 3 sections. The peach color is equipment that we either built at Morehead State or was commercially available. The section in blue is DSN supplied equipment, and the section in green is at DSOC, the Deep Space Operations Center at JPL, and of course the missions are on the far end. In the blue section, basically we implemented a Block 6 receiver and transmitter system, but sort of a light version of that system. We're single channel as opposed to a 3-channel DSN system. So it's a little bit simpler, a little bit less complicated, but it is the DSN, based on the DSN Block 6 system. On the peach side, the Morehead State side, we have a lot of custom systems. The RF feed was custom. We didn't use the SMC, the station monitor and control system, because we couldn't generate all those data points, the metadata points from our system. So we have a much more limited system we call monitor and control, rather than network monitor and control, actually. So it's a little bit simpler system, but it basically functions just like a DSN station. The next slide shows you what we look like from the user perspective. We've been trying to develop a system that's completely transparent to the user. So the missions do everything they would normally do. In fact, in some cases, they might not even be aware that they're using DSS-17 as a station, except that it takes us about twice as long to pull down the data volume as a 34-meter beam waveguide. But the missions provide an ephemeris to the SPS server. They pull their data from the SPS server, and they interact with DSS-17 just as they would with any other DSN station. The next slide just shows that we are on the NASA mission backbone. Have some more interesting things to talk about, so I'll just skip that. But we are behind the NASA firewall and directly on the NMB. And in the next slide, you can see the performance characteristics. So it's really pretty darn good for a 20-meter class antenna system. So we are exclusively X-band for deep space. LNA temperatures under 20 Kelvin. The total system temperature is about 90 Kelvin, about 63 dBi gain. And I'll show you some charts for G over T here in a minute, but reasonably good performance for a 20-meter class system. In the next slide, you can see how we compare to a 34-meter beam waveguide. And our rule of thumb is that we're basically 10 dB less in terms of G over T. We're 5 dB less of gain, but a 5 dB higher noise figure. So that adds up to about 10 dB. So whatever performance you get from a 34-meter beam waveguide for your particular mission, basically subtract 10 dB, and that's what we could give you. The good news is we can stare for longer typically because we're less subscribed. And so what we make up, what we can't make up for in performance, we can to some extent make up for in much longer track times. The next few slides just show some of the empirically measured performance metrics. We did characterize the system as carefully as possible with empirical measurements of G over T and the IRP. Some radiometric measurements, empirical measurements of the horizon mass. So most of the data that you'd be interested in if you're considering DSS 17 for a mission is available, and it's actually available through the DSN. The next couple of slides we'll go through quickly. The next slide shows you the stability of our KPA for ranging. So it's a fairly stable system over time. Again, we have to operate for about twice as long to get the same volume of data, whether that be radiometric data or telemetry that a DSN 34-meter station would have. So we need to really pay attention to stability. In the next slide, I think we can just basically has the same data. I think probably the thing about this slide, the takeaway here is that if you work through the math, we have about 1 meter accuracy at the moon for ranging. So not bad.
Ben?
Yep.
Ben, you have 1 minute.
1 minute. I tell you what, let me skip down to slide 21 if I could. And let's see, let's go. Yep, a couple more to be cognizant of everybody's time. One more, please. And we'll end with this, just a milestone for the timelines here. So we've gone through all the design reviews, all the hardware and software implementation. We just sat for operational readiness review back in August, and so we are ready to support the Artemis 1 stations and Capstone coming up. And let's see, I think I have, in the 10 seconds I have left, if we could go to the last slide, which is sort of the future. Let's go one more, please. Sorry, two more. One more and I'll end here. Yep, just one more, please. Next slide. Yep, there we go. So the future is looking at some future implementations like DTN experiments and OSPA, which we're both capable, which we're capable of currently now. So I will end there since I'm out of time and be happy to answer questions during the panel. Thank you.
Okay, at this point, we'll start a question and answer. If I can get all the speakers to please come up. So I'll be monitoring the WebEx in case there's any online questions, and Craig will be walking around the room with the microphone. So if you have a question, please just raise your hand and Craig will get to you.
This question pertains to anybody dealing with these launches and the delays, especially with dealing with a cryocoolant like liquid nitrogen. How do you accommodate that if you have to bottle up a CubeSat and it sits on the launch pad for 6 months?
Okay, can you hear me now? Yeah. I was gonna say that is a good question. So we haven't really planned for that. One of the other challenges, or one of the other things that scares us a bit is that more so than keeping the nitrogen, in a tank for 6 months, is how do we keep the rest of the satellite? If we have a surface that is at, say, 50, 80 Kelvin, how do we keep the rest of the satellite warm or within operating temperature ranges for the other instruments? And that is something I think that goes hand in hand with what you're asking, I think. To answer your question, yeah, it's we haven't figured it out yet. So
From my previous life, don't use helium. But no, seriously, the gases, some of the larger molecules, valves are good enough to last for that period of time. It's been my experience.
I'll add one more comment, if I may, on the behalf of the Lunar Ice Cube team. It really is an extraordinary challenge. We're likely to have sat on the launch pad, where at least stacked on the rocket for a year or more by the time we launch Artemis 1. And so a lot of systems I'm certainly worried about. We do have a closed cycle cryogenic infrared spectrometer that is a problem, but also even the propellant. We use iodine, solid state iodine as a propellant, and over time, things like that tend to vaporize, at least even at room temperature. It can cause clogging of valves and that sort of thing. So, to the extent that you can with environmental protection, dry nitrogen backfill, we've done everything we could. But then when you sit on the launch pad in an uncontrolled environment for a year, that's really a challenge. So I'd love to hear any other ideas, because I don't think we figured it out, certainly on our end.
Actually, I have a question for Ethep. So in your presentation, you showed kind of a one-to-one interaction between your docking and the recognition. Have you given any thought into how, if you have multiple CubeSats, how it would recognize or determine which one to dock with?
Yes, so we have given some thought to it. Obviously, we haven't gotten more than 2 satellites or more than 2 systems to communicate still. But what we are leaning towards is to actually have some sort of coding going through. So we are dealing with RGB LEDs. So there is potential to encode more messages in terms of color coding. So some sort of like a header or a calling mechanism when there is multiple satellites talking to each other for coordination would be the way we are leaning towards. But we will learn more only when we are doing it. For now, it's only one-on-one communication, but once we master that, we'll be going to more than 2 satellites at a time.
Thank you.
So I have a question for Leonard. Is there an aspect ratio between the size of objects you can capture versus your satellite?
All right, so the question is, how large does the grappler have to get around the debris object? And so more work to be done in that area, but the obvious half answer is you have something that's at least half the circumference of the debris object you're intentioning, you're trying to get. So I've got the ability now to figure out what that actually needs to be over an ensemble of shapes. That work is yet to be done.
Okay, thank you for that.
Actually, I'd like to follow up that with Leonard. So in your presentation, you stated that these shape metals, basically you manipulate them through heating. Have you ever thought, put any thought how to maintain that in space, those temperatures?
Okay, yeah, so the concept is that when it's cooled, when it's not heated, it is in a closed environment, it's in a closed shape. So that in order to open it up, it's heat, but then let it cool down and it circle the object. So by default, it's going to circle.
I have a couple of questions. One is for Ben. I was wondering, it's Alessandra. I was wondering, you said that now you're going to support more EM Artemis missions, and I was wondering if now you guys are built within the scheduling overall of DSN, or if you guys are scheduled separately, and how that works for the missions when they, gonna use the different services.
Mhm. Hi, Alessandra. I wish I were there to hang out. So we are scheduled through the DSN scheduling service. Even missions that are not part of Artemis 1, like Capstone, will use the DSN scheduling service. And so, I just got to say one quick thing about DSN scheduling, which to me, initially, I thought would be, relatively uninteresting because, you're scheduling time on assets. But actually, every aspect of DSN is fascinating, even the scheduling. I mean, it uses artificial intelligence algorithms all the way through, almost attorneys fighting in a back room for the missions to advocate and everything in between. So it's a pretty incredible scheduling process. And so to be part of that's pretty cool, and to have learned a little bit about how these assets are scheduled is amazing. But in summary, we're actually scheduled by the DSN through the DSN scheduling and mission scheduling services.
Thank you. And then I have one about for Dennis on the interference for the IQ separator and the algorithm. I know you developed it for Iris. I was wondering if this was something that you guys are scaling and using on other radios like Snapdragon or UST, or if it's just something that is peculiar with Iris.
Yeah, so this task really sort of split the two separate tasks up. So the recorder was for Iris, but the software algorithm or studying the algorithm was generic. So I did that on synthetic data. So if you have a processor that can do large enough matrix multiplication, then you do it. Of course, you need the hardware to record the samples. So you need both. But in general, the higher level algorithm is generic. Yes, a future radio that has even more power, we would love to implement it on that. I think it will become more important. And as we see with the Mars helicopter, we're becoming more comfortable with flying very powerful computers. And so the answer is yes. Yeah, this will hopefully be implemented on other platforms.
My question is for Jeff and the F Prime software. You mentioned in your talk outreach to younger students. And I guess my question also comes from like a rapid prototype and sort of from someone who uses ROS a little bit. Does F Prime either have a desire or a plan to implement wrappers in another higher level scripting language like Julia or Python to sort of effectuate more rapid development and lower the barrier to entry a little bit for younger students like undergraduate level?
Yeah, we think about that. One of the issues we face is that, we have really limited resources. So ultimately, a lot of the capability that we implement in F Prime, ultimately, we prioritize the needs of JPL. So we're not really resourced to. I've had this conversation with a number of educators. I've been actually using the previous conference as an opportunity to kind of reach out and talk to students and faculty about this issue of using F Prime as an educational tool, because F Prime is not developed as an educational tool. It's a professional, application, or it's a professional grade product line, which we make available to students to use. And so it's great that we've been able to work with a number of universities. Georgia Tech was the first to deploy a CubeSat using F Prime. So we know it's possible, right? There's a bit of hand-holding because there is a significant learning curve associated with F Prime, and we're well aware of that, and that's why we do the workshops. So yeah, we do talk about we do talk about and think about what kind of if we were to think of it more from an education standpoint, or maybe more broadly, just reduce the barrier to entry, right? What are some of the things that we could do? Python is one of them. And I've talked internally about having basically a Python implementation of the framework. Now, so I put this out there. I mean, the software is open source, so it's not something that we at JPL actually have to do. I'm actually looking for collaborators. And one way we would achieve this is actually by working in collaboration with somebody, or if somebody were to come to us and say, you know, this is what we want to do, and can you help us with that? That's something we certainly do. I think Georgia Tech has done some work in that area. That they have what they call G prime, right, which is essentially a Python, some kind of Python instantiation that's very similar to F prime. But I don't think it's designed to really be that. I'm not sure really if it. I don't think it's something they were considering to release open source. Another area that we've been looking at, which isn't so much to reduce barrier to entry to F prime, but to acknowledge that there are users, and there are other users that want to be working in the area of flight software, but not necessarily in C++, is integrating with ROS. We have, a sister organization in our, at JPL, which is the robotics, section. It's close organizationally to the flight software section. And so, of course, they do a lot of development in ROS. And so we've been talking about, we haven't really gotten very far. There's just been some initial conversations. There's definitely some interest there in figuring out how we can tie the two together. It's not something we're pursuing, that heavily at the moment, but we've had a number of discussions. There's also this initiative that is being championed, I think, by Blue Origin called Space ROS. So, I mean, ROS in and of itself is highly popular. It's not really, ROS 1.0 is not really well suited for flight applications, but there's definitely interest in using ROS because of the user community associated with that, and there's interest in integrating that with F prime. So yeah, we're at the point where we're having discussions, but we still have a long way to go before we get on to any kind of, but thank you for the question.
There's a question over here. Over.
Yep, this is a follow-on for Jeff. Help me understand, how does F prime, what's the ecosystem F prime and CFE CFS look like?
Okay, this is how I know that there's people paying attention to software in this group. That is the question that we do anticipate anytime we talk about F prime is, where does it stand with CFS? So for those of you who don't know, CFS stands for the Core Flight System. It's a very prominent flight software architecture and framework that was developed by Goddard, has been around for a while, so it has a lot of traction. It's used widely among a number of NASA centers. And so here we are at JPL with our own thing. So, why do both exist, and what's the difference? I think that's the nature of your question. Sure. So, even though CFS has been around longer, it's been available open source longer, F prime really represents our flight software heritage at the lab. So it's something that's always been developed, independently and concurrently with CFS. It's just, it reflects, our flight software values, if you will, right? And so there are some key architectural difference that's reflected in those values. The primary difference, and this is getting a little bit into detail of the architecture, but the messaging scheme that's used on F prime is fundamentally different from CFS. So F prime has a point-to-point messaging scheme. So if you recall in my presentation when I showed the architecture, and there was like an example of components linked up together to form a topology. Those connections were direct. So a component, an input port on a particular component connects directly with an output component. An input port on a component connects directly with an output port on another component. And in CFS, you would, if you were to envision the type of topology that you see in a prime, where you have a bunch of components that are all directly connected to each other, in CFS, you would take those connections, you would take them out of the direct connection among components, and you would insert a message bus in the center of all that, so that all the connections, essentially all the messaging connections, go through this messaging bus, which serves as a router. And so that's a fundamental architecture difference, and it has ramifications, in terms of applicability and ease of use and things like that. In the case of F prime, having point-to-point messaging gives you increased performance, and you get better control over timing. And it's really important for us, given the variety of applications and deployments that we need to support. So for example, a message in a messaging bus architecture, as I understand it with CFS, it doesn't really support very well running in what we call bare metal with no operating system present. And that's something that, you know, given the applications we're using with our Prime, where we're focusing on small scale and hyper small scale systems, we're running on these low power microcontrollers. So the Mars helicopter is an example. It had the Qualcomm, you know, Snapdragon deployment, which is the most powerful processor ever delivered to deep space. And you could easily run CFS on that, I think. I think the timing would be okay. But on the TI microcontroller, you wouldn't be able to do that. And so since we need both, that Mars helicopter is an example where CFS, we wouldn't be able to deploy fully on that system. Another area where there's some differences is in terms of the tooling that's provided. I mean, CFS certainly has been around longer and it has a wide array of tooling, but I think it's kind of dispersed and managed kind of independently. For one thing, you know, the tooling that comes with F Prime is centrally managed, and as I said, it's comprehensive and it covers fundamental phases of software development. And we have this special emphasis on software modeling. And as far as I know, I mean, with the domain-specific language with FPP, as far as I know, there's really no other product out there, certainly open source product, that is as comprehensive with the tooling and has that modeling front-end capability. So those are a couple areas where they're distinct.
Hi, it's Chris Casa from JPL. My question is for Ben Malfers. Hi, Ben. On the DSS 17, I'm wondering if you are still using the UHF portion of it for tracking satellites. And if so, in the next 5 years, say, how many % of it do you expect to be a clientele from UHF customers and X-band similarly? Thank you.
Hi, Chris. Good to hear your voice. We are out of the UHF business, to be honest. There is a fair amount of interference these days in UHF, and we sort of struggled. We have this beautiful quadrature array feed that we developed for the 21 meter. It's a great system. But over time, there has been a lot more interference in UHF, and we were able to deal with it mostly by bandpass filtering and that sort of thing. But now there are a number of really very powerful UHF signals that are in band and much more difficult to deal with that sort of RFI. And so we're exclusively X-band for deep space, and we're doing some S-band work. Mostly for calibration work for LRO, but we're primarily devoted to X-band these days, and for the foreseeable future with DSS 17.
Any other questions in the room?
Yep, I have a question for Massimo. So you mentioned that the ranging for the visible light communication is about 50 meters. Oh, yeah. Oh, sorry. But what kind of time frame are you looking to between that 50 meters for the time to dock?
So we chose 50 meters because we chose 50 meters for identification, actually. Ranging, I'm pretty sure there are like other ways where we can go for much larger distances. Basically, if we use GPS, we could range from anywhere. There is also radar, but we chose 50 meters because the commercial LEDs that we are able to easily procure and test based on the calculation, basically the inverse square law, that we were able to do it only for 50 meters for now. There are other technologies in LEDs, especially emerging, which will increase the range, but that's the reason why we chose 50 meters. So once we are able to identify the target CubeSat, then the ADC system will basically align the two together. And that's when the ranging system, especially the low cost and low profile ranging systems, will be able to perform the ranging. So that's why we chose 50 meters. As far as the time frame goes, it depends on the propulsion system that's on board itself. We haven't done too many calculations on that yet. So far, we've only been doing bench testing with 6 degree of freedom robotic arms. So yeah, the propulsion systems sizing that will be done once we are in much, let's say, once we are much more developed with the ranging itself.
Okay, thank you for that.
Okay, are there any other questions in the room?
Hello, I'm CJ Howdigi from the University of Arizona, and my question is for Leonard Vance. I had a question on the shape memory alloys that you plan on using. Do you plan on testing a variety and seeing their material standards, or are you have a specific alloy in mind already?
David has been working on specific out, and we are in the process of doing trade studies to figure out. It's a question of the application temperature and shaping of the alloy itself. It's also possible because we don't really need very much tension. Things that we're grappling, we only need to hold a single number of newtons. It's also possible that there's plastics that do the same thing. So that's in the trade space as well. So more to come. We've just started.
Any other questions? If not, then I'd like to thank our presenters once again. And we will take our break now and reconvene at 4. Thank you very much.